All right, so now we'll say something about stability regions, A stability and L stability. Okay, so in particular, let's try to make this a little bit concrete by considering a specific numerical method. So let's consider the trapezoidal rule. Okay, and let's look at the stability analysis of this. Right, so the trapezoidal rule says that Zn plus 1 is equal to Zn plus h times f evaluated at Zn plus f evaluated at Zn plus 1. Okay, and whenever you want to do stability analysis, it suffices to apply the method. It's like to this model differential equation which says that z dot is equal to lambda z. Okay, so let's see what happens when you do that. So you get Zn plus 1 is equal to Zn plus h, right? Lambda Zn plus lambda Zn plus 1. Okay, and I want to see how Zn plus 1 can be expressed as some multiplicative factor applied to Zn. All right, so I'm going to take the Zn plus 1 term to the left, and then, sorry, there's a h over 2, and then keep the Zn terms on the right. Okay, so this gives me 1 minus h lambda over 2 multiplied into Zn plus 1 is equal to 1 plus h lambda over 2 applied to Zn. So another way of saying this is that Zn plus 1 has the following amplification, right? So it's 1 minus h lambda over 2, sorry, it's 1 plus h lambda 2 over 1 minus h lambda over 2 multiplied into Zn. Okay, and then this is what we call the stability function, R, which depends on h lambda. Okay, so another way of saying this is that R of z is equal to 1 plus z over 2. All right, so I'm going to try to distinguish my z's and the 2's. All right, 1 minus z over 2. Okay, so so you want so the stability region is the domain. It's like in which this stability function has a modulus which is less than equal to 1. Okay, so the stability region is the set of points, right, z in the complex plane, such that the modulus of R of z is less than equal to 1. Okay, so so let's try to draw that. Okay, so this is the set of, again, z in the complex plane such that the modulus of 1 plus z over 2, right, 1 minus z over 2, right, is less than equal to 1. And I can multiply on both sides, so this gives me z in the complex plane such that the modulus of 1 minus z, or 1 plus z over 2 is less than equal to the modulus of 1 minus z over 2. Okay, and then of course I can multiply both sides by a factor of 2. This is the set of z in the complex plane such that 2 minus z is less than equal to the modulus of 2 plus z and 2 minus z. All right, and then this is something it's like which I can then write down the, it's like I have a geometric interpretation of that. Okay, so as you might expect, z is a point that's like on the complex plane. All right, I'm going to look at the locus of points which satisfies that inequality, right? It's the real and imaginary part of z. And of course, you can interpret this as the distance between z and the point 2. All right. And then this, of course, is the distance between z and the point minus 2. Okay. So what this is telling you is that the distance from z to the point 2 is greater than the distance from z to the point minus 2. So, okay, and of course the points where it's like the distances are equal is of course nothing more than this bisector of the line which connects these two things. And then what you have is that you want the z's where the distance to 2 is greater than the distance to minus 2. So you're looking at this left half plane here. Okay, so what this tells you then is that the stability region for the trapezoidal rule is the entire left half plane. Okay, so this is the stability region. Okay, and then you can ask, well, what happens if you would apply this to some other method? It's like which we might be familiar with. So let's continue along these lines. Okay, so for implicit Euler, okay, you have that Zn plus 1 is equal to Zn plus h lambda Zn plus 1. Okay, so I've already applied it to this model problem, z prime is equal to lambda z. All right, so again, I move, it's like the Zn plus 1 terms to the left-hand side. I get 1 minus h lambda Zn plus 1 is equal to Zn. Okay, so Zn plus 1 is equal to 1 over 1 minus h lambda Zn. Okay, so the stability function, if you will, are viewed as a function of h lambda. So if you write this just as z, this is 1 over 1 minus z. Okay, and again, the stability region, right, let's call that D, right, is the set of points z in the complex plane such that the modulus of the stability function is less than or equal to 1. Okay, so that's equal to z in the complex plane such that 1 over 1 minus z modulus the whole thing is less than or equal to 1. Okay, and you can write this as the condition that 1 is less than or equal to the modulus of 1 minus z. Okay. All right. So let's see what you get. So what is this saying, right? So this is saying that the distance between z and the point 1, okay, so I have a point 1, z and the point 1 is is greater than or equal to 1, okay? So let's just look at the equal to 1 case. That's of course just a circle of radius 1 centered about the point 1, and you want all the z's, it's like where the distance from 1 is greater than or equal to 1. So you're looking at this region here, which is outside the unit circle, centered about 1. Okay, so this is the stability region. It's like for the implicit Euler method. Okay. Yep, so it's the exterior, if you will, of this disk of radius 1 centered about 1 in the complex plane. All right, so with these in mind, it's like we're now able to state for you sort of a more general notion of stability. So if you will, it's like the reason why these stability regions are interesting and important, right? One of the things you want to have is that, you know, if you have a differential equation which looks like y prime is equal to lambda y, all right, and you allow lambda to be any complex number, then the set of exact solutions, right, which are asymptotic to 0, or at least for which the origin is stable, right, are in the left half plane, it's like of the complex plane. And you might be interested in numerical methods which are unconditionally stable, which is to say that irrespective of what positive time step you take, it would have the property that when applied to a system of linear differential equations which have this origin being stable property, that the same thing holds for your numerical method. So what that basically leads to is this idea of astability. Okay, so you have this idea of astability, and what astability is about is that so a method is astable, right, if the stability region includes the entire left half plane. Okay, so what does it mean for the stability region to include the entire left half plane? That means that the numerical method has the origin as being a stable point if you let h times lambda be in this left half plane. And as I said before, if lambda on its own is in the left half plane, that corresponds to exact solutions for which the origin is stable. And so if you let h be any positive number, positive real time step, then h times lambda will remain the left half plane as long as lambda is in the left half plane. So more or less, the one way to sort of think about this is that this idea of astability means that if you were to apply this numerical method to with a time step which is positive to a system of linear differential equations whose eigenvalues are in the left half plane, for which the exact solution has the origin as a stable point, then your numerical discretization is also going to respect that property and it's going to have the origin be stable as well. Okay, so this motivates, if you will, this definition of astability. And then there is a more sort of sharper, if you will, or sort of more restrictive condition known as L stability. So L stability is concerned with the asymptotic behavior, if you will, as this z goes to infinity, right? So L stability is concerned also, if you will, with the asymptotic behavior, right, as z goes to infinity, and a method is L stable. Okay, if the first thing is that it is astable, so of course it's a more restrictive condition, and there's something about the asymptotics. It's like of the sort of stability function. Okay, so r of z goes to 0 as z goes to infinity. Okay, so this is a much more restrictive condition, but this notion of stability is important when we're considering it's like certain classes of differential equations, typically stiff problems. So let me just stop here for now.